All right. Once again, good morning. Hope you guys are doing well. It is Friday, so I hope nice weekends, restful weekends are ahead for everyone. Today, lost my train of thought. Sorry. First note actually is I'll get your graded labs to you as soon as I can. Hopefully, I'll be able to send you your scores by about early next week, and like your physical copy is yours to collect after I grade if you want it. I can, if you don't necessarily want the copy but just want to know, what factors wound up affecting your score, I can talk through any of that with anyone at any time. For today, in terms of lessons, I want to begin looking at the science of and the math behind phase change. It's our next thermal energy related topic. First, as usual, I want to open the floor up to any questions or issues you might be having. I do advise you to have been working on the Chapter 11 homework, and today hopefully we'll cover some more formulas and concepts that'll help you to fill that out. So chime in if there's any questions or issues at this particular time, and if not, we'll move on with phase change. All right. So, let's see. Make sure I'm sharing my screen. All right. So, phase change is just the term used to describe something you've definitely dealt with before. That is to say, the changing of the state of matter. Freezing, melting, evaporating, and condensing are all phase changes because they change the state of matter that something is currently in. And before we look into the math of how and why those things work, I want to look at a few statements and see from what perspectives might they make sense. Because I want to look at some things that might not immediately sound right. The statements currently on screen say, melting is a cooling process, freezing is a warming process, condensing is a warming process, boiling is a cooling process. You don't necessarily need to say anything if you don't want to, but I want you to just ponder for a second. Do these sound right? Do these make sense from any perspective that you've thought of before? And depending on how much chemistry or physics you might have had before, you might be able to see the way in which these are true. Let's just start at the top. Let's start with the idea that melting is a cooling process. If something is currently melting, most people would think of that as the object getting warmer. And you are correct. From the perspective of, say, an ice cube, the act of melting would be the ice cube getting warmer and melting into water. That is, from that perspective, this first statement, melting is a cooling process, wouldn't seem right. But for that ice to melt into water, it needs to absorb thermal energy from its surroundings. If you're holding a piece of ice in your hand and it starts melting, you, the person holding it, are losing thermal energy. Your hand gets colder as the ice melts. So from your perspective, from the perspective of the person holding an ice cube, melting is a cooling process. There's melting going on in your hand, and it's making your hand colder. So all of these statements are from the perspective not of the object undergoing the phase change. They're from the perspective of the surroundings of that process. If you're holding the ice cube, you are part of its surroundings, and as the ice cube melts, you get colder. Because for melting to occur, an object has to absorb thermal energy from its surroundings in order to complete that phase change. The way that phase changes work is that they're basically the next step up from thermal expansion. If you take a solid object and you heat it up, it will expand. We've demonstrated that mathematically. We've shown it in lab a few times. As that object heats up and expands, if you keep heating it up, it's going to keep expanding. That's because its particles get further and further apart as it absorbs more thermal energy. At a certain point, its particles are just going to get so far apart that it can't maintain a solid shape anymore, and it literally melts because its particles are too far apart to be a single solid object of definite shape anymore. It's literally thermal expansion part 2, and this continues if you take the liquid and continue heating it up until it starts to evaporate. If you heat up the liquid, it too will expand to a certain point, and if you keep heating it up past its evaporation point, its particles will keep getting further and further apart until they literally bounce off of each other so hard they rip free from each other and turn into vapor that shoots off into different corners of the room. When you're boiling water and steam comes out of the surface of the water, that's literally water molecules rocketing out of the water's surface fast enough to not fall back down. And the steam occupies a much bigger volume than the water it originally had. So, phase change is basically just thermal expansion. And in order to cause that phase change, an object has to either absorb enough energy to make it happen or release enough energy to make it happen. Melting is a cooling process because it absorbs energy from its surroundings. The opposite is true for freezing. In order to freeze something, that object has to release thermal energy into its surroundings so that it can become colder. If you put something into your freezer, the whole point of the freezer machine is it takes the objects that are inside of it, have their thermal energy extracted. And that thermal energy is then, through the machinery of your freezer, sent somewhere else, so it's not in the freezer anymore. So, when you put something in the freezer, you technically make the freezer warmer until the freezer kicks on and starts to extract all that extra thermal energy. The act of freezing warms up the surroundings of whatever was doing the freezing. Moving on, condensing is a warming process. This is what happens when you take an ice-cold drink outside and steam starts condensing into water on your glass. There's water vapor in the air. It's going to touch the ice-cold glass of your drink, and that steam is going to turn back into water vapor when it touches your cold beverage cup. But as it condenses back into water, the cold thing it's touching is your water glass, and therefore that steam is putting thermal energy into your beverage so that the steam can successfully turn back into water. And this entire process, besides making your glass wet, also warms up your drink. It literally puts thermal energy into your cold beverage, melting your ice faster, and just making the whole experience a little less fun. The last one here is boiling as a cooling process, and this statement describes why humans sweat. When I was a kid, I always used to wonder why humans sweat when they're hot. Like, what is the purpose of that? Why is this a benefit to us? I'm already hot and miserable. Why do I also have to be drenched and sticky, especially living in the South where the air humidity is already miserable? Why does there need to be even more water present? The reason is, in order for water to evaporate into steam, it has to absorb thermal energy in order to do so. So when you sweat, there's now water on your skin. It wants to evaporate because you're warm, it's a hot summer day. In order to complete that phase change, it needs to absorb thermal energy from somewhere, and since it's touching your skin, it absorbs it from your skin. So, in a weird roundabout way, water evaporating off of your skin makes you colder. And that's why humans sweat. It's kind of a weird roundabout way to get there, but there is a reason for it, despite the discomfort. So, these statements are true. They're just not from the perspective of the object in question. Instead, these are from the environment's perspective, and these inform some various descriptors that you may have heard before, depending on how much physics or chemistry you've had in the past. There's two terms that scientists like to use to describe whether a process absorbs thermal energy. Whether a process absorbs thermal energy or gives off thermal energy. And those words are endothermic and exothermic. If something is endothermic, it absorbs thermal energy from its surroundings. Depending on your chemistry experience, you might have triggered some chemical reactions that, as a part of the reaction, it absorbs thermal energy into itself, and therefore it feels colder to your surroundings. Meanwhile, an exothermic process releases thermal energy into its surroundings. Icy hot patches use chemicals to do both of these things. One part of the reaction absorbs thermal energy, and that's the icy part. A separate part releases thermal energy, and that's the hot part. So, to apply these statements to the phase change processes, melting and boiling are endothermic because they absorb energy, whereas freezing and condensing are... Wait, did I get that backwards? Yes, freezing and condensing are exothermic since they give off thermal energy. So, it's just to kind of get a little vocab framework in to set the stage for the math behind phase change. Please let me know in any way, shape, or form if any of these statements dang it. Alright, how long was I gone?
Maybe like 5 minutes.
Fantastic. What was the last thing you heard? I don't know how much talking I did in 5 minutes. Okay. Okay. I guess I'll just go over what I think was within the last 5 minutes very quickly. Melting is a cooling process because it has to absorb energy from its surroundings in order to melt. Freezing is a warming process because it has to give off thermal energy in order to freeze. So the purpose of the freezer machine is to take energy out of your cold food and send it somewhere else. Condensing is a warming process, and that's why water condensing onto your iced tea glass makes it warmer. Boiling is a cooling process, and this is why humans sweat. Humans sweat because if there's water on your skin, it's warm water that it wants to evaporate. That water needs to absorb thermal energy out of your skin in order to turn into steam. So sweating does cool you off, which is something that always confused me as a kid. But there's surprising amounts of math behind it. So, these statements are from the perspective of the environment, not from the object that is undergoing the phase change. And we use the terms endothermic and exothermic to describe whether or not they are giving off energy or absorbing it. Endothermic processes include melting and boiling. They absorb heat. Exothermic processes include freezing and condensing. They give off heat as those processes go on. Certain other chemical reactions can behave similarly, like icy hot patches. They have chemicals in them that either absorb heat for the icy part or give off heat for the hot part. Make sure I didn't lose signal again that time. All right. Let me know if any of those statements you would like revisited or re-explained. I went over them pretty quickly because I'm kind of frustrated I lost signal there. Sorry. And with that, the point of this was to kind of set the stage for the phase change math to follow. Now, the math behind phase change, it's weird, but it's also pretty straightforward in that literally you just have to multiply two numbers together to figure out how much thermal energy is required to complete a phase change. So say you have some amount of ice in your hand and you need to turn it into water. In order to melt that ice, you need to add a certain amount of thermal energy to it in order to complete that phase change. The amount of energy required is determined by this formula here. It's really the same formula twice. Q equals mass times latent heat. So Q is still thermal energy. This is the thermal energy change needed to complete a certain phase change. That's equal to the mass of the object times the latent heat of the object. The mass is just how much material is present. If you have a bigger block of ice, it takes more energy in order to melt it. So the mass term is important. But so is this latent heat term. And kind of like with specific heat, every different material has a different latent heat. It's just a constant that determines how much energy is needed to specifically phase change that specific material. So we have a new table here that has the different values on it. This column right here, latent heat of fusion, that's the LF term right here. I'll explain the difference between LF and LV in a minute. Latent heat of fusion specifically refers to how much energy is needed to either melt something or freeze it. So for example, say in some very strange scenario, you had a block of solid helium, frozen solid helium, and a block of solid aluminum. Aluminum has the biggest latent heat value currently on this table. It's to a factor of times 10 to the fifth, whereas helium has the smallest. It's of a factor of times 10 to the third. This means that comparatively, if you compare helium to aluminum, if you had a solid block of these two different materials, it would take less energy to melt the helium than it would take to melt the aluminum, just by virtue of what they're made of. And this is one of the contributing factors as to why helium melts at a really low temperature, and therefore you don't really find solid helium on planet Earth. It's really easy to melt helium because it has a low latent heat, and the ambient natural temperature of planet Earth is enough energy to get it to and keep it at those temperatures. Making sure I didn't lose signal again. Meanwhile, aluminum has a much higher latent heat. It takes more energy in order to melt the aluminum instead. The aluminum has a higher latent heat. It takes more energy to melt the aluminum, and that's one of the reasons why it's a lot easier to find solid aluminum on planet Earth. It just takes more energy to cause aluminum to melt. So every different material has a different latent heat. You don't have to memorize any of them. You'll have access to this table. This entire semester is going to have a bunch of dedicated constant charts, and you do not need to memorize any of them. The way that you would use this formula, if, say, you had a block of aluminum that you wanted to melt. If you wanted to melt aluminum, the first thing you need to do is warm up the aluminum to get it to its melting point, which is specifically 660 degrees Celsius. First, you got to get the aluminum up to that temperature. Once it's at that temperature, you'll then need to add even more thermal energy to get it to perform the phase change. So you have to add energy to warm it up to that temperature, and then you have to give it more energy on top of that. And this formula, Q equals ml, tells you how much of that extra energy you need to add. If you had a 1 kilogram block of aluminum that was already at 660 degrees Celsius, its mass, 1 kilogram, times its latent heat of fusion. So if you had 1 kilogram block of aluminum that was already at 660 degrees Celsius, you would need to add 3.97 times 10 to the 5th joules of thermal energy to it to complete that phase change. Subsequently, if you had molten aluminum at 660 degrees Celsius that you wanted to turn back into solid aluminum, that is the same amount of energy that you would need to remove from it. This formula and the fusion constant pulls double duty as the amount of energy you need to add to something to melt it and the amount of energy you have to remove from something in order to freeze it, because those two processes are the same in reverse. So, for this formula, if you plug in a positive Q, that will tell you the amount of heat needed to melt in a certain amount of something. Negative Q is the amount of energy you need to remove in order to freeze it. So the fusion column pulls double duty for both melting and freezing. Fusion refers to any of the phase changes between solid and liquid, either direction. The second version of the formula, LV, refers to the latent heat of vaporization. And this is a separate list of constants that, rather than referring to melting and freezing, refers to boiling and condensing. There's different constants for the evaporation processes from liquid to gas than there is from solid to liquid. So if we had liquid aluminum, and we wanted to evaporate it, we'd need to heat that liquid aluminum up to 2,450 degrees, and then we would have to add this much energy to 1 kilogram of molten aluminum to turn it into gaseous aluminum. Now that's a really high temperature, and that's a lot of energy. That's to the point where you don't find that on Earth, and so that's why most humans, I don't think, have ever dealt with gaseous aluminum. At least I hope not. But the reverse would still be true. In order to condense gaseous aluminum back into liquid, this is the amount of energy per kilogram you would need to remove from it. So the only things that you really need to have memorized about this is when to use the formula and when to use each of the different latent heats. Latent heat of fusion refers to any solid-liquid change, freezing or melting. Latent heat of vaporization refers to any liquid-gas change, evaporating and condensing. Again, you will always have these tables. You will not need to memorize any of them. Any issues thus far? Just chime in. All right. Now, these formulas themselves, they're like just the formula. It's just 3 terms. It's just multiplication. It itself is pretty straightforward. There is a little bit more nuance in sorry. I'm just going to move on to the next visual and explain that as I go. To try to use this information practically, let's say, for example, you have some amount of negative 10 degrees Celsius ice. You have ice, it's below freezing, and you want to turn that ice all the way into 110 degrees Celsius steam. So this ice is going to go through every phase change. You're going to increase its temperature by 120 degrees. In order to figure out how much energy that takes, we need to go through every phase and every phase change along that journey. So let's just start from the beginning. We're starting with ice. And this graph that's currently on screen, its purpose is to represent how much thermal energy is needed to get a certain object to a certain temperature and to complete the phase changes through that temperature. So let's just start with below freezing ice. We're starting at the very beginning. Now the way this graph is set up, the horizontal axis is energy added. So as we scroll to the right along this axis, we're continuously adding energy to the material. The vertical axis is temperature. So as you add thermal energy to something, its temperature may or may not actually go up. If you have ice, and that ice is below freezing, so we're starting at negative 10 degrees Celsius ice. If you're holding that ice and you add thermal energy to it, if it's below freezing, it's not going to immediately start melting, right? If it's below freezing, the first thing it's going to do is warm up until it hits that freezing point. Because in order to melt the ice, you have to get it to 0 degrees Celsius in the first place. So if it's colder than that, the first step is adding thermal energy using MC delta T to get it from negative 10 up to 0. And so the first part of the graph, which is admittedly the smallest part of the graph, is this little slanted line that represents adding thermal energy to ice to warm it up to its melting point. But something weird happens once you actually get it into its phase change temperature, once you get the ice up to 0 degrees Celsius. When ice hits 0 Celsius, does it magically immediately melt? The answer is no. I promise you the answer is no. Additionally, once ice starts melting, does its temperature keep rising as it melts? The answer is also still technically no. I currently have ice water right here, and the ice in this cup is at 0 degrees Celsius. The water in this cup is at 0 degrees Celsius. And yet, the water is not immediately freezing into ice, and the ice is not immediately melting into water. You've dealt with this every time you've ever had an iced drink. The point of the ice is to get the drink down to 0 degrees, and the phase change of the ice melting into water does not happen immediately. If you get ice up to 0 degrees Celsius, it could stay as ice. It may never melt as long as it stays at 0 Celsius. In order to actually cause the phase change, once it's at 0 Celsius, you then have to add thermal energy to it using the Q equals ml formula to get it to perform the phase change. And while it's phase changing, first of all, the change doesn't all happen all at once. The energy will be added at a certain rate, and therefore the ice is going to melt at a certain rate. It doesn't all happen immediately. But furthermore, while that phase change is going on, the ice isn't getting any hotter. It is melting, but its temperature isn't rising until it's done changing phase, until it's done melting. And so how this graph shows that fact is that even though we're still adding energy, the graph is still scrolling to the right, the temperature stopped increasing. This line became flat, and the temperature axis does not rise again until the ice is completely done melting. 0 degrees Celsius is the highest temperature that ice can exist at. at least that's the highest temperature the ice can be. But that's also the lowest temperature that water can be. The melting point is the point at which the two phases can coexist. And the phase change doesn't happen all at once. The temperature will remain constant until the phase change is done. Because in order to do the phase change in the first place, well, if the ice was colder than freezing to start with, you had to add energy to get it to freezing. But once it begins melting, all the thermal energy you add after that point just goes into the melting process. That's what this formula is. This is just Q equals ml is the melting process. Adding thermal energy after you get it to its melting point causes it to melt. It doesn't cause it to get any warmer. It'll only start warming up once it's done melting. And this is why ice is good at keeping your drink cool, because as long as there's still ice in your cup, it'll still be 0 Celsius. Once all the ice is gone, then it'll start warming up again. Its temperature will start changing. So, say you've melted your ice. You've used Q equals ml to figure out how much energy you needed to melt it. You've added that much. The ice is now gone. It has now become 0 degrees Celsius water. It's still 0 degrees Celsius, but it's absorbed enough energy to become water. Now that it's all water, if you continue adding more thermal energy, its temperature will begin rising again. So the next phase, we're back to Q equals mc delta T to add thermal energy to the water to warm it from 0 to 100. Once it's water, adding energy will increase its temperature again, as one would expect, until you hit water's boiling point. Once the water hits 100 degrees Celsius, its temperature stops increasing again, and it starts boiling. And like with the freezing process, its temperature isn't going to increase again until it is all entirely steam. Once you hit that boiling point, we're in the phase change zone now. Any amount of energy you add just goes into causing the phase change. So, boiling water will remain at 100 degrees Celsius until it's done evaporating. In lab yesterday, we used this fact to our benefit in that we had boiling water on our lab table and we were using it to keep our metal samples at a constant 100 degrees Celsius temperature. The water could not get any warmer than that until it had all become steam. As long as there was water left, that water was going to be 100 degrees Celsius. This is the same when you boil water to cook in. Boiling water is a nice, convenient way of cooking things because we know exactly what temperature it's going to be. It's not going to change until all the water's gone. And if all the water is gone, then you've burnt whatever you were cooking in the first place. So, the water to steam phase change, it stays at 100 Celsius until you've completely added enough thermal energy to turn all of it into steam. Once all of it is steam, then we can use Q equals mc delta T for steam to make the steam a higher temperature. So to figure out the energy needed to perform this phase change, you have to go through every single step. You have to use Q equals mc delta T to warm the ice up to freezing. You have to use Q equal ml to melt the ice. Then you have to use Q equals mc delta T to warm up the water, then Q equals ml to evaporate the water, and then Q equals mc delta T to warm up the steam. All of those steps have to happen chained one after another, and therefore the energy total, the ultimate total amount of energy this takes, is going to be the sum of all those individual steps. Because you have to do all of them in order to make it happen. It's cumulative. And I will demonstrate what that might look like on a separate slide as we do to work an example. One thing that I want to mention briefly is that the fact that steam, in order to turn the water into steam, you had to add a lot of thermal energy to it. This is one reason why steam is very, very, very dangerous. If you've ever heard someone warn you about steam burns at some point, this is the reason why. Steam inherently has more thermal energy in it than water does. If you don't do this, obviously, just I need to say that out loud. If at any point, however, your hand was submerged in water, if at any point your hand was, heaven forbid, submerged in boiling water, that would not be as dangerous as your hand being blasted with steam. Because the steam inherently has more energy in it. So if the steam is touching you, it is able to put more energy into your body as it condenses into water. If steam touches you, it'll give energy to you until the steam is 100 degrees Celsius water again, and then you're still touching 100 degrees Celsius water, because the steam just turned back into 100 degrees Celsius water. And then the steam could have even been a higher temperature to start with. Boiling water is always capped at 100 Celsius, but steam can be hotter than that and inherently has more energy. This is why steam burns are dangerous, and please be careful around steam. Kind of a weird aside there, but it's a point that's worth making if you're at any point involved in some industrial amount of steam. So, to go from ice to steam, you have to go through all those various steps and add all the energy requirements together. The opposite is true if you wanted to go from steam all the way down to ice. You need to figure out how much energy you need to remove to cool your steam down to 100 Celsius. Then you need to figure out how much energy you need to remove to turn 100 degrees Celsius steam into 100 degrees Celsius water. Then you need to figure out how much energy to remove to turn 100 degrees Celsius water into 0 degrees Celsius water. Then you need to figure out how much energy you have to remove from 0 degrees Celsius water to turn it into 0 degrees Celsius ice. Then you have to figure out how much energy to remove to turn 0 degrees Celsius ice into negative 10 degrees Celsius ice. It's the same chain of events, just in reverse, and you end up with a negative answer because you had to remove all of that thermal energy. That's a lot of steps. It's a lot of individual parts. If there's anything you'd like me to repeat, please let me know. Usually in person, I like to make this graph a lot bigger and trace along it with my hand and doodle on it. So if some amount of that visual representation has been lost in internet translation, please let me know. I've been talking a lot. I need a sip of water. Okay. So, I've been hand waving a lot and describing a lot of steps that one needs to do. I'm now going to actually show them written down in 2 examples. First example, how much thermal energy needs to be removed from 0.1 kilograms of 115 degrees Celsius steam in order to turn it into 25 degrees Celsius water. So we're starting with steam, we're going to turn it into water. Excuse me. All my work... oh, geez, pardon me. All of my work for this one is on the next slide, so I'm going to tab over to look over it. This includes my work for the next part, but we're just going to focus on the steam part for right now. So, delta Q steam, the amount of energy needed to remove from this steam to turn it into the water that we want. The first step this is MC delta T. We want to cool the steam down from 115 down to 100. Because in order for it to perform the condensation, it has to be at 100 degrees Celsius first. So the first step is the 115 degrees Celsius steam needs to become 100, just 100 degrees Celsius steam. That's the first step. The next step is actually, once you get it to 100 degrees, you have to remove enough thermal energy to perform that phase change. So the next term here is ml, Q equals ml, the phase change formula, mass of steam times the latent heat of vaporization of steam. And I'll show you where to find that on the table from the other slide in a second. Once you've completed the phase change and taken out all the energy needed, the last part, you will end up then with 100 degrees Celsius water that you need to reduce the temperature of using MC delta T again. Except this time, we're using a delta T ending at 45, starting at 100, and you have to be mindful of which specific heats you're using at which specific times. This earlier one here, where the steam is cooling down from 115 to 100, you need to use the specific heat of steam. And yes, H2O's specific heat does change depending on what phase it's currently in. It's kind of frustrating. Over here, once it's in the state of water, then you would use the specific heat of water. So, this is the daisy chaining, the summation of all the individual parts. This is the MC delta T for cooling the steam, the ML for condensing the steam, and then the MC delta T for cooling the water. We can start plugging in all the things that we know. All of these M mass terms here is the steam's mass, and we were told the mass of steam. It's kind of hard to determine the mass of a gas, but it's not impossible. So for all of the mass steam terms, we can plug in 0.1 kilograms. We know the change in temperature that the steam has to undergo to start becoming water. So that's a change of -15. That will ultimately make this entire first term a negative, which makes sense. You need to lose thermal energy to cool down. And then we need to look up the specific heat for steam. I'm going to tab back several times to try to show the table that has that information. This is a previous example that has the specific heats chart on it. Specific heat of steam is listed here somewhere. Here it is. Steam 2010 joules per kilogram degree Celsius. It is less than water. It's kind of weird. They have separate ones though, and they are different. Pretty radically different numbers actually. Liquid water is the only one with a tremendously huge specific heat. Both steam and ice have much lower ones for reasons even I'm not completely certain of. But this is a specific heat of steam. We should also make note of the specific heat of water. So we'll plug in steam's 2010 right there. And that'll be everything for the first MC delta T part. Next is ML. Specifically, we need the latent heat of steam. So backing up a little bit. Latent heat of vaporization. Specifically, you want to use latent heat of vaporization for any liquid to gas or vice versa process. Doesn't matter which direction you're going in, as long as it's evaporating or condensing, you want to use latent heat of vaporization. So, water, scroll over to look at latent heat of vaporization for water, and that number is 2.26 times 10 to the 6th power. So that's the number we bring over to plug in for the latent heat of our steam. And then the last term is the change, the MC delta T for reducing the temperature of the 100 degrees Celsius water we'll end up with down to 45 degrees Celsius. That'll use the same mass. Even though it's changing state, it's still the same amount of material, so the mass doesn't actually change. It's the same mass all the way through. Now that it's water, we can use the specific heat for water again, 4,186, and then its temperature change, going from 100 to 45, is negative 55. And that's every variable, every term. We are set now to try to find the total amount of energy loss required to complete this entire process. There's one small hiccup to be aware of in this whole chain, and it's the fact that the latent heat formula, the ML, does not inherently have any way of telling you whether or not it should be positive or negative. ML itself is just the amount of heat needed to complete the phase change. The formula itself doesn't really care or have a mechanism for is that phase change adding heat or removing it. So within this formula, within my math here, I had to manually put a negative sign in front of that because I knew when writing this that to turn steam into water, you have to be removing thermal energy from it. So it's kind of frustrating, but using this formula does require a little bit of awareness in that regard. You do have to be aware of what direction the change is going in and apply signs accordingly. But for this particular case, that's all the information we needed. That's every variable filled in. We can find a complete final number here, and that means that the Q needed to remove from this steam to turn it into our end goal of 45 Celsius water is negative, because we're removing it, 252,036, 38 joules. So that's all of the needed energy transfer. That is objectively a lot of math and hand waving. Let me know any issues, if any, as they come up. I'm going to tab back briefly now to look at the second part of this question. How many grams of ice would be needed to absorb the above calculated thermal energy if the ice starts at -6 Celsius and ends at 45 degrees Celsius water? So realistically, if we were actually to perform this experiment, we would have a box of steam, and we would be putting ice in the box, sealing it, and eventually, just due to the natural thermal energy exchange between the two, we would end up with a box of 45 degrees Celsius water. The steam will condense down into 45 degrees Celsius water. The ice is going to melt and become 45 degrees Celsius water. They'll end up at the same point. And we want to figure out how much ice is needed to absorb the energy total that we found a second ago. And this process will look pretty similar to the other part, because to lay out our formula, we need to show all of the temperature changes and all of the phase changes. So delta Q ice, to get the ice to the point where it will melt, we have to use MC delta T to get it to 0. One thing to note here is that its final temperature is 0, its initial temperature is -6. Final minus initial, 0 minus -6 will become +6. Temperature is increasing. That part of the formula will be positive. Then comes the ML term for actually melting the ice. So mass of the ice times the latent heat of fusion for H2O. And then lastly, the energy required to warm up 0 degrees Celsius water into 45 degrees Celsius water. So laid out very similarly. The only main difference here is we're going to be using different specific heats and different latent heats because there's different states involved. And we actually have an answer for Q this time, and we're solving for M instead. So, the steam needed to lose this much thermal energy to become the water that we needed. That means the ice has to absorb that much thermal energy. It's gaining the heat, so we'll plug the same number in for delta Q ice. It's just positive instead. The only unknown we really want here is the mass of the ice required. So all of the MIs I have left as MIs. It's the same mass of the same amount of ice all the way through. It's the same mass of material even after it melts. Excuse me. So all the MIs in every single part are the same, regardless of what step you're on. To increase the ice's temperature, we have the mass of the ice times change in temperature of the ice times the specific heat of ice. From the table from earlier, specific heat of solid ice is 290 as opposed to steam. I keep saying 100 instead of 1,000. I'm sorry. Specific heat for ice is 2,090 as opposed to steam's 2,010 and water's 4,186. So we're going to use the 2090 here in this first term. For the LF term, mass is still unknown. We're keeping that the same. And we'll need to find the latent heat of fusion for water. Again, if it's any change involving solid and liquid, if it's melting or freezing, we need to use fusion, not vaporization. So I'll tab back to the other chart here. We'll look for water, specifically latent heat of fusion this time. That constant is 3.33 times 10 to the 5th instead of the one we used before. So that is the value I have plugged in for LF of ice. And then the last term is increasing the temperature of our newly melted water. Mass is still unknown, but now that it's water, we can use water's specific heat, and the change in temperature at this point would be positive 45. As many steps as this takes, as many parts as this that there is, the only unknown left is MI. So my next line is simplifying most of the complex terms. There's now 3 terms on the right that have an MI in them, and since it's just MI, none of them are missing an MI, none of them have MI squared, it's just MI. We can add them all together normally. So these 3 things can add together into one bigger MI term, and we can use division to solve for the needed mass of ice. It'd be 0.47 kilograms of ice. So that much ice in a box with our original amount of steam, they would eventually totally combine together into 45 degrees Celsius ice. There's a lot of chains and parts to questions like this, so working them kind of requires you to get into a rhythm, to think in terms of all of the steps of the chain that you'd need to go through. I've been talking a lot, so I imagine you need a break from listening and I need a break from speaking. So right now, we call a quick pause, we call a break. Take some time to digest this information, glance over the homework to see if you can start applying it, and I'll be here for the next hour if you pop back in with any questions that have come up. Let me know if there's any questions you have right now, be they about this or anything completely random. But if not, feel free to take a quick break. I know I could certainly use one myself.
I don't have any questions right now, but thank you.
You're welcome. And if you don't pop back in today, have an excellent weekend. Rest well.
Thank you. You too.
Thanks.